Hi, I'm Anna Leushchenko, mobile development expert, GDE in Dart in Flutter from Ukraine. And I'm here to talk about Dart Garbage Collector. The Garbage Collector, or GC, serves as an automatic memory manager. The Garbage Collector manages the allocation and release of memory for an application. For developers, this means that you don't have to write code to perform memory management tasks. Automatic memory management can eliminate common problems such as forgetting to free an object and causing a memory leak, or attempting to access memory for an object that has already been freed. The garbage collector provides the following benefits: frees developers from having to manually release memory, allocates objects on the managed heap efficiently, reclaims objects that are no longer being used, frees their memory, and keeps it available for future locations, and provides memory safety by making sure no two objects will have to fight for the same memory slot. Like most modern languages, Dart has a generational GC, which is based on the empirical observation that the most recently created objects are also those most likely to become unreachable quickly. So all new objects are getting allocated together in one group, one generation. Then there is an assumption that the longer an object has been on the heap, the longer it will probably stay there. So objects that have survived one or more garbage collections are then moved to a group with older objects, another generation. Dart runtime environment uses a memory pool called heap for objects allocations. Roughly speaking, the heap consists of the first or new generation or new space, young space or nursery, and second or old generation or old space. When the application starts, it naturally starts allocating new objects. If an object is less than 256 kilobytes, the heap tries to allocate it in the new generation. The new generation follows the Cheney's algorithm and is said to consist of two semispaces. Only one half is used at any time, one being active, the other inactive. New objects are located in the active half, and once that's filled, live objects are copied from active or from semispace to inactive or to semispace, ignoring dead objects. The inactive half then becomes active and the process repeats. In fact, if we check Dart VM implementation, and I spent quite a lot of time recently digging into the source code, most of the time there is only one active semispace. New objects are allocated here in the simplest way, called the bump pointer allocation. Basically, objects are located in a contiguous space in memory next to the previously located objects. The bump pointer points at the beginning of the available space. When the next object is written, the bump pointer is incremented to point to a space immediately after that object. This approach makes the allocation process very fast. However, it does not allow to deallocate individual objects or reclaim the memory region for a no longer in use object. The default value for the initial size of the new generation semispace is 1 or 2 megabytes depending on the device architecture. The thing is, some parts of the Dart virtual machine behavior are configured with flags. CLI lets you set any VM flag if passed before the Dart source file. But you would have to be writing an embedder to do this. It's impossible to change it in the runtime because virtual machine is already initialized. The initial size of the new generation semispace is configured through this flag. Imagine now that during an attempt to allocate a new object, there is no space available in a semispace. The first thing the new generation will try is to acquire a new page. The thing is, generation space is not really contiguous. It consists of chunks of 512 kilobytes called pages. Each page has a pointer to the next page, so they form a linked list. So the new generation will try to acquire a new page, link it to the last existing page, and allocate a new object in it. If it could not allocate a new page because it has either reached a maximum size or we are out of memory, the next thing it will try is to run a garbage collection in the new generation and attempt allocating an object once again. If the allocation in the new generation still fails, even after garbage collection is complete, the heap will attempt to allocate an object directly in the old generation. This is only one of the scenarios when the garbage collection can be run in the new generation, and we'll see later what are other reasons for that. For simplicity, I will return to a visual representation of a single contiguous space and add more objects to make it more fun. We are now looking at a parallel Stop the World semi-space Scavenger. It is called Stop the World or blocking because no mutations on the heap's objects graph are allowed while the GC runs. At this point, a new semi-space is created. The currently active semi-space is now called the From semi-space, and the new one is the To semi-space, to which we are going to copy a live objects. So, how live objects are detected? To understand that, I need to tell you about GC roots. These are static fields, local variables, method parameters, basically everything on the stack, and a thing called handles. The Dart virtual machine does not know which objects in foreign languages contain pointers into the Dart heap, including the virtual machine's own runtime implemented in C++. Foreign languages reference Dart objects indirectly through handles, which can be thought of as pointers to pointers. This way, when GC moves the object during the collection phase, it only needs to update pointers in handles. And let's also look into what is a three-color marking garbage collector. Three sets are created. The white set, or condemned set, is the set of objects that are candidates for recycling. The black set is a set of objects that are reachable from the roots and have no outgoing references to objects in the white space. Objects in the black set are not candidates for collection. The gray set contains objects reachable from the roots, but yet to be scanned for references to white objects. They cannot be garbage collected and will end up in the black set after being scanned. In main algorithm, initially the black set starts as empty. The gray set is a set of objects which are directly referenced from roots, and the white set includes all other objects. Every object in memory is at all times in exactly one of three sets. The algorithm proceeds as follows. Pick an object from the gray set and move it to the black set. Move each white object its references to the gray set. This ensures that neither this object nor any object it references can be garbage collected. Repeat the last two steps until the gray set is empty. When the gray set is empty, the scan is complete. The black objects are reachable from the roots, while the white objects are not and can be garbage collected. Cheney's algorithm, on which the Dart VM new generation is based, implements such a three-color marking algorithm. Imagine this is our semi-space state just before the GC run. Objects 1 and 8 are members of the root set. Objects 3 and 4 are accessible from object 1, object 6 from object 3, and objects 10 and 12 are referenced by object 8. At this point, all objects in the From semi-space are members of white set. The first members of the gray set are root set members. They are copied into the To semi-space. Once an object is copied, the source object in the From semi-space contains the forwarding pointer to the new location. The To semi-space is meant to contain members of the black set and gray set. It contains two pointers. The scanning pointer points to the end of the black set, so objects below it belong to the black set. And the free space pointer points to the end of the gray set and the next free space. This means objects between the scanning pointer and the free space pointer are members of the gray set still to be scanned. The first member of the gray set is object number 1. It references objects 3 and 4, so they are copied into the 2 semispace and forwarding pointers are installed. The algorithm moves any white objects to the gray set by copying them into the 2 space. Objects 3 and 4 are now part of the gray set. We have completed scanning the first object, which means it can be moved to the black set by simply moving a scanning pointer over it. The process repeats. The next item in the gray set is object number 8. It has a reference to objects 10 and 12. So they are now copied to the 2 semispace. And pointers are updated. Next, we look at object number 3. It has a reference to an object 6, so it again is copied to the 2 semispace. Next movements of the scanning pointer do not produce any new references to scan. When the scanning pointer reaches the free space pointer, the gray set is empty and the algorithm ends. By this time, all live objects are copied from semispace to semispace, and the from semispace can be safely deleted. The garbage collector also logs collection stats and updates the estimate of scavenger speed. In fact, in this case, when the new generation garbage collection was triggered because an object failed to allocate, after it is complete, either full garbage collection or one of its phases can also be triggered in the old generation. But more about old generation later. Now we have a brand new active semispace with a few survivors already taking space. These are all candidates for promotion to the old generation on the next garbage collection run. The application continues to allocate small objects in the new generation until we again reach the point where a garbage collector decides to run a collection. It again detects all live objects. If the expected garbage percentage is under a certain value, it means we had too many survivors during the last collection. This value is defined with this flag, the default value for which is 90%. As a reaction, the new 2 semispace grows compared to the previous size by this flag value. The default is 2. The maximum semispace size is regulated by this flag, the default value for which is 8 or 16 megabytes, depending on the device architecture. We already know what happens with the new survivors that should be copied to the 2 semispace. But objects which survived this and the previous collection should be copied into the old generation. A question is, how exactly a garbage collector will know how many collections an object has survived? Well, that's easy. After the previous collection has been completed, when the semispace contained only the survived objects, it has installed a special pointer at the end of this list. So, every object under this pointer is a survivor and should be promoted. The last thing I'd like to mention about the new generation is why the scavenger is called parallel. By default, there might be several worker threads competing with each other to do the job of moving an object from semispace to the 2 semispace, or promoting the object from the new generation to the old generation. The number is defined with this flag, and by default there are 2 of them. By now we have already discussed several scenarios when objects get into the old generation. The most common cause is by surviving 2 or more garbage collections in the young generation. Each scavenger worker has its own local free list, from which they take space when promoting objects from the new generation to the old generation. Free list is basically a list of chunks of free available memory. If a chunk is quite big, this Scavenger uses the same bump pointer allocation algorithm for individual allocations. So, if the object is under 64 kilobytes, the Scavenger will try to allocate it via free list. If this attempt fails, it will try to grow the old generation by 1 page. Surprise, surprise! Old generation also consists of linked pages of 512 kilobytes. A new page will be added to a free list, and it will repeat an attempt to allocate an object. For objects larger than 64 kilobytes, it will immediately try to acquire a new large page and allocate an object there. The old generation has an additional linked list of large pages dedicated to large objects. This way, the old generation may grow up to a value of this flag, the default for which is 1.5 or 30 gigabytes, depending on the device architecture. The virtual machine limit is slightly below operating system limit to increase the likelihood of falling gracefully with a Dart out of memory exception instead of SIG abort. If there is still not enough contiguous space in a free list to accommodate an object, it will try to wait for any running phases of garbage collector and repeat the attempt. If allocation fails again, it will run the garbage collection in both generations and repeat an attempt once again. Then it also may try to force grow the old generation and also try to aggressively collect the garbage before finally giving up. If during this evacuation phase an object failed to be promoted, it will be instead copied to the 2 semi-space together with other newcomers. Once the GC decided to run a collection in this generation, the first step is the same: decide which objects to keep and which to erase, which is done at the marking phase. All heap objects have a single word header, which encodes the object's class, size, and some status flags. It also contains a bit called the mark bit. At the start of a collection cycle, all objects have their bit cleared. We are now again looking at the 3-color marking algorithm. Similar to the young generation, the algorithm starts at the roots, which is in our case objects 1 and 8. If a root object is an old generation object and its mark bit is clear, the mark bit is set and the target is added to the marking stack or the gray set. The collector then removes and visits objects in the marking stack, marking more old objects and adding them into the marking stack, until the marking stack is empty. At this point, all reachable objects have their mark bits set, and all unreachable objects have their mark bits clear. The marking phase is non-blocking for most of its time, which means memory mutations are allowed. If a new object gets allocated in the old generation during the marking phase, it is immediately marked as belonging to the black set with the marking bit set. The new generation objects do not participate in the marking phase, and pointers to the new generation objects are ignored. Instead, all objects in the new generation are treated as part of the roots set. The GC visits the new gen objects as roots at the end of the marking phase and sets more marking bits. Treating new gen objects as roots has an advantage of making collections of the 2 generations more independent. In particular, the marker never needs to dereference any memory in the new generation. You see, garbage collections in the new and old generations can happen simultaneously. So, this approach helps avoiding data race issues and the need to pause or synchronize with garbage collection in the first generation. It has, however, the disadvantage that no single collection will collect all garbage. An unreachable old generation object that is referenced by an unreachable new generation object will not be collected until GC collects the new generation object first. And unreachable objects that have a generation crossing cycle will not be collected until the whole subgraph is promoted into the old generation. Normally, this is not an issue because new generation garbage collections run much more frequently than in old generation. Now that all objects are marked, there are two possible scenarios. The lightweight is called sweep and the hardcore is called compact. During the sweeping phase, the GC walks through a list of all generation pages and looks at objects marking bit on every page. If GC meets a marked object, it just clears its marking bit and leaves it as is. It, however, adds all the unmarked objects to the free list. If it appears that all objects on some page are inaccessible, the page is deallocated and is released to the operating system. In addition, some large pages can be truncated. As you can see, the old generation may not only grow, but also shrink in size. The sweeping phase allows refreshing free lists with known slots of available memory. But as you can imagine, over time the heap becomes fragmented and requires compacting. For that, Dart VM garbage collector also implements a sliding compactor algorithm. In this algorithm, each page is divided into blocks, and each surviving object is related to a block where its header belongs. It will calculate the size of surviving objects in a block and find free space to allocate all these objects together. It keeps cursor pointing to the next free and next live chunks and repeatedly moves the next live chunk to the next free chunk, one block at a time. So, during compaction, all live objects in the same block will slide such that they all end up on the same page, and all gaps within the block will be closed. Free space at the end of a page that is too small for the new block is added to the free list. All empty pages will be freed. We already know what objects might get allocated directly in the old generation if at the time of allocation the new generation was full. In addition, objects that are bigger than 256 kilobytes also end up straight in the old generation. We saw that GC has mechanisms to run garbage collection at times where it could not allocate new objects. But, in fact, it is much smarter than just sitting and waiting for this situation to occur. There is a notify Intel callback that notifies virtual machines that the embedder expects to be idle until deadline. Flutter, for instance, calls this between frames with the amount of deadline left until the next frame. Can you imagine? With Flutter aiming to provide at least 60 frames per second, frames need to render approximately every 16 milliseconds. The virtual machine may use this time to perform garbage collection or other tasks to avoid delays during the execution of Dart code in the future. This gives the garbage collector a window of opportunity to run its collection phases without impacting the performance. Let's see what happens during these calls. This is rough pseudocode. First, GC decides if it wants to collect garbage in the new generation. And it may want to do it for two reasons. Either the new generation is getting full, or it makes sense to run the idle garbage collection in the old generation, because it only has a couple of free pages left. And because, as we saw previously, the entire new generation is treated as roots while collecting the old generation, it is beneficial to minimize its size. So, if the answer is no to both cases, no Scavenger will happen. But if the answer is yes, it will happen only if it is estimated to complete before the deadline. But how does it know how much time it will take to run a collection? Well, during each GC run, it collects stats about the speed and the total size of objects it collects in a microsecond. For the initial run, it takes a conservative value of 40 words per microsecond. After the first scavenge, it will instead use a value based on the device's actual speed. Typically, the new generation garbage collection takes tens of milliseconds. Next, the algorithm checks if it still has time for collection in the old generation, starting from the most expensive one, Mark and Compact. The decision is made based on the usage ratio and fragmentation state of the heap, and also if there is enough time to complete this process before the deadline. As I said, this is rough pseudocode, because in fact more checks are involved, like no concurrent sweeper is running. The Mark Compact is preferred over other old generation garbage collection techniques if there is enough time, since it removes fragmentation and frees up most memory. But it is roughly twice as costly as Mark Sweep. Overall, old generation runs can take hundreds of milliseconds. Otherwise, the algorithm checks if the heap is in a good shape. If the old generation has grown significantly since the last time we checked, there is a probability that the next scavenge promotion will grow it even more. So, even though the following GC may exceed the ideal deadline, it performs Mark and Sweep on old generation. And finally, if there is still work to do because the available space in old generation is less than 5% or than the size of the new space, start a concurrent marking phase or complete the work that has been started previously. The next old space allocation will trigger this work anyway, so we try to pay at least some of that cost with idle time. Fascinating, isn't it? This will not trigger a collection if the heap seems to be at an appropriate size, even if there is substantial garbage that could be collected to free memory. There is another callback, Dart notify low memory, which Flutter calls when the operating system sends a low memory warning. It is a fairly expensive call that aggressively compacts all memory. Oh, I believe after learning about all this stuff, you might have some questions. Can I force GC to run? No. Can I disable GC? No. Can I do at least something about GC? No. The takeaway I want you to have is that Dart has an automatic memory management system that is your friend. It is smart enough to deal with tons of small objects a Flutter app may allocate, handle garbage, resolve circular dependencies, cross-generational references, and does it in a very delicate way, trying to avoid blocking apps as much as possible. Today we have covered a lot, but not everything. There are interesting details in each of these areas, like special large old generation pages, special treatment for images, isolates, and more. I hope there will be more interest in the community about this topic, and we'll see more talks about Dart Virtual Machine Garbage Collector.